This Ohm's law works because electric voltage propels charge through a conductive path. The clever bit here is that true physical resistance remains completely constant regardless of how much electric current flows through the material. In elementary electrical circuits, voltage equals current multiplied by resistance, establishing a fundamental linear empirical relationship that engineers rely on daily. German physicist Georg Ohm first published these exact proportional circuit measurements in his landmark 1827 research treatise after rigorous testing. However, when testing diverse real-world electrical components under actual operating conditions, experimental measurements frequently seem to contradict this straightforward linear relationship. Early experimenters noticed that calculated numerical ratios between measured voltage and current often shifted dramatically as current levels increased through specialized circuit devices. If dividing instantaneous operating voltage by measured current yields a continuously changing number, the underlying physical component appears to blatantly violate Ohm's constant resistance rule. This apparent discrepancy caused massive confusion among early telegraph engineers because assuming fixed resistance produced severe calculation errors in real physical telegraph networks. Many 19th century researchers initially believed that Georg Ohm's formula was either fundamentally flawed or merely a highly restricted approximation valid only in specialized laboratory setups. Without a rigorous scientific distinction between static circuit ratios and true constant ohmic behavior, predicting practical electrical circuit performance across varying power loads remained notoriously unreliable. The resolution lies in recognizing that Ohm's law specifically describes a precise physical material property rather than serving as a universal definition for every electronic component. When a component's internal resistance changes due to thermal heating or strong electric fields, the mathematical formula still defines instantaneous static DC resistance as voltage divided by current. However, materials that exhibit current-dependent resistance are formally categorized as non-ohmic elements, which does not invalidate Georg Ohm's primary discovery for true ohmic conductors. Georg Ohm's original historical treatise explicitly demonstrated that pure solid metallic conductors maintain a strictly constant proportional voltage-to-current relationship under uniform thermal conditions. By carefully controlling and isolating operating temperatures, precise modern laboratory testing confirms that linear voltage-current proportionality holds remarkably accurate over many orders of magnitude. We explain this mechanism at a documentary level, carefully preserving scientific qualifications and physical limitations stated directly in foundational historical and modern literature.
The bigger problem was explaining how microscopic charge carriers inside a solid metallic conductor maintain this perfectly constant physical resistance under intense driving fields. It appeared almost impossible that trillions of continuously accelerating subatomic electrons wouldn't accumulate massive kinetic energy and fundamentally alter internal drag as current surged. Classical electromagnetic theory struggled to clarify why doubling external applied voltage precisely doubles electric current without altering the material's intrinsic internal resistance property at all. If free conductive electrons accelerated continuously without atomic resistance feedback under an electric field, internal current density would surge non-linearly over time instead of stabilizing instantly. Engineers and theoretical physicists urgently required a localized vector field formulation to directly connect macroscopic circuit measurements with subatomic charge carrier transport dynamics. Physicist Gustav Kirchhoff ultimately solved this theoretical challenge by reformulating Ohm's empirical relationship into a rigorous vector field equation applicable at every point in space. In vector form, localized current density, J, equals electrical conductivity sigma, multiplied directly by the local electric field vector E at any specific point inside the conductor. Conductivity sigma represents an intrinsic material-dependent parameter defined mathematically in electromagnetics as the exact reciprocal of the conductor's physical volume resistivity, represented by ρ. At the microscopic subatomic scale, applied electric fields accelerate free electron drift until frequent collisions with vibrating thermal crystal lattice ions rapidly scatter their kinetic energy. These hyperfrequent atomic collisions establish a steady terminal drift velocity, causing internal current density J to scale in perfect direct proportion to local electric field intensity E. Because the fundamental microscopic collision rate depends strictly on atomic lattice structure and ambient temperature, electrical conductivity sigma remains remarkably constant across varying current levels. To bridge this continuous vector field model back to practical macroscopic circuits, engineers integrate vector equation J equals sigma E along the full physical geometry of a uniform conductor. Integrating the local electric field vector E along the total physical length L of a wire yields the scalar voltage difference V measured across its two terminal endpoints. Concurrently, integrating current density vector J across the conductor's total cross-sectional area A yields the total macroscopic electric current I flowing through the complete circuit. Combining these geometric integrals with volume resistivity ρ leads directly to the familiar macroscopic scalar resistance equation, R equals resistivity ρ times length L divided by cross-sectional area A.
This mathematical transition rigorously proves that macroscopic resistance R depends strictly on physical material composition and geometric dimensions, remaining completely independent of total operating current. When applied circuit voltage increases, total current rises in exact direct proportion because the microscopic lattice scattering process operates with identical statistical efficiency across all field strengths. In non-ohmic components, like semiconductor diodes or incandescent bulb filaments, intense self-heating or junction field shifts alter atomic lattice dynamics, causing highly dynamic variable resistance. However, for standard metallic conductors operating at stable temperatures, linear voltage current proportionality remains remarkably robust, providing reliable and predictable electrical engineering behavior everywhere. Mastering both the macroscopic scalar equation, V equals IR, and Kirchhoff's vector continuum equation, J equals sigma E, enables precise engineering of advanced high-power electromagnetic equipment. This counterintuitive engineering mechanism reveals that constant electrical resistance is not a magical material property, but a statistical equilibrium derived from microscale atomic lattice collisions. By distinguishing constant material resistance from dynamic static ratios, 19th century physicists transformed practical electrical work from unpredictable empirical trial into an exact predictive mathematical science. From delicate microelectronic silicon processing chips to massive high-voltage electrical transmission grids, linear voltage current proportionality remains the primary cornerstone of modern power control. Gustav Kirchhoff's vector field formulation perfectly bridges microscopic subatomic lattice physics with everyday macroscopic circuit design equations used across global modern technology. Georg Ohm's initial empirical measurements provided the bedrock scientific insight that continues to dictate how electrical energy is conducted, managed, and harnessed around the globe. Understanding how constant conductivity governs current flow unlocks the foundational electromagnetic physics that powers our interconnected high-tech world with absolute mathematical clarity.